I'm Shogo Ochiai from Tokyo University of Science in Japan. In this video, I'll talk about new approach to dishonest majority secure multi-party computation for malicious adversaries when n is smaller than 2k-1. This is the outline. Background. In recent years, too much wide variety of data are collected in many ways, such as IoT devices. Then, these data will be used for some statistics, machine learning, and so on, in order to create new businesses. However, big data may contain individual data, confidential data, and so on. Therefore, the way for protecting this data is highly required to utilize them. Multiparty computation, MPC, is one of the ways for protecting and calculating data. MPC enables a set of people to compute a function f with their private inputs S1, S2, S3 without revealing any inputs but output. This is a basic model of MPC. Next, we explain the secret sharing scheme. In general, KN threshold secret sharing scheme is often used for MPC. In this scheme, first, secret holder distributes secret among n servers. In detail, secret holder generates n shares of secret, then send one share for each of the servers. Second, the secret can be reconstructed by k or more shares. So, in order to reconstruct the secret, the receiver should select k servers and ask for sending its shares. One important thing is that any information doesn't be leaked from less than k shares. Next, we'll explain the representative method of KN threshold secret sharing scheme that is proposed by Shamir in 1979. In this scheme, shares are generated by k-1 degree polynomial that its constant will be set as the secret. The share of server Si is a point on the graph as shown in the picture. In this scheme, linear operation on shares and constant can be performed as follows. Moreover, multiplication on shares can also be performed as follows. However, after multiplication, the degree of the polynomial increases from k-1 to k-2. This means the threshold k increases to k-1 after multiplication. Therefore, in the setting n is smaller than 2k-1 in Shamir's scheme, the multiplication result cannot be reconstructed because sufficient shares don't exist. This limitation of n and k doesn't only occur in the Shamir scheme. In MPC, it is said that unconditionally secure MPC doesn't exist for n is smaller than 2k-1. Therefore, some approaches to solve this problem have been studied for years. Now we introduce two approaches that are both using the scalar times share approach. At first, multiplication triple. Multiplication triple is a set of three values, f, g, and f times g. As this equation, multiplication result a times b can be calculated by only linear operation. Second, TS method. This approach was proposed by our research team and has been used for our MPC method. In TS method, secrets and results are hidden by multiplying random value. So, one when a pair of multiplied secrets can be temporarily reconstructed and used as a scalar value. This table shows security properties of three methods which can be performed in the setting of n is smaller than 2k-1. In this table, red-colored properties mean superior to others, and blue-colored properties mean inferior to others. As shown in the table, representative MPC method SPDZ has security against malicious adversaries, while TS method is only secure against semi-honest adversary. So, in this study, we are mainly focusing on the security improvement of TS method while maintaining its superior properties. Before I explain our method, let me introduce the basic approach of TS method. We use nearly the same approach of TS method for proposed method. As shown in this slide, in TS method, secret is hidden by multiplying random values, and the calculated result is also hidden by multiplying a different random value. These are basic approach for secure addition and multiplication in TS method. Regarding both calculation, the multiplying random values alpha and beta are both replaced with the same random value delta. Next, I explain commitment scheme. This scheme is used for realizing integrity of our proposed method. The commitment scheme is a two-phase cryptographic protocol. In the commit phase, the commitment of X is calculated for the input X. In the open phase, the value X will be opened from the commitment of X. This scheme has two important characteristics. First, hiding. Hiding means the commitment of X doesn't reveal any information of X. Second, binding. Binding means different commitment will be calculated from different input. There are two types of commitment schemes. First, unconditional hiding and computational binding. Second, computational hiding and unconditional binding. The former type is often used in MPC because what the most important is to hide secret in MPC. And we also use the former type in our proposed method. From now, we explain the proposed method. As I said, proposed method is mainly focusing on improving security of TS method. Therefore, its approach is nearly the same as TS method. Our main contribution is realizing integrity while maintaining the advantages of TS method. So, we slightly changed the way of hiding secrets, and we adopted commitment scheme. The MPC model in our protocol is as shown in this slide. Firstly, some users who have secret distribute their own secret by secret sharing scheme to the servers. Secondly, servers compute required function F by interacting each other. In this computation, any secret is not revealed because they are distributed by secret sharing scheme. Finally, the server sends its shares for the result to the receiver. Then the receiver can reconstruct the result. Next, we explain core idea of a proposed method. In distribution phase, the secret is related to random value by addition in two ways like that. These two values will be computed independently. Therefore, the result is also related to random value in two ways. In reconstruction phase, the correct random values are prepared by using commitment scheme. Then, the protocol verifies whether two results are same or not. This is the core idea of a proposed method. In fact, in distribution phase, the values are hidden by multiplying random values like TS method, like that. As I explained, these are used for computation and reconstruction. And we need 2 additional values. These values are used for multiplication. And each alpha will be distributed by secret sharing scheme, like this method. These are basic approach for secure addition and multiplication in proposed method. In the same way as TS method, the multiplying random values are replaced with the same random value as shown in the equation. From now, we discuss security of a proposed method. We define these 3 requirements for security. First, confidentiality. This means the secret of honest users is not leaked to anyone. Second, integrity. This means that the honest receiver obtains the correct result except for negligible probabilities. Finally, availability. This means the protocol can be applied for any n which is equal to k or more. However, I omit the discussion of confidentiality and availability because these are nearly the same as TS method, and our main contribution is realizing integrity for TS methods. Although I explained only one verification in the slide of core ID of a proposed method, there are 2 verifications in our protocol. First verification is to detect some part of attacks, and the second verification is to detect rest of attacks. At first, I explained the first verification. This verification is to guarantee that each input was distributed correctly to some extent. The meaning of to some extent here is this verification cannot detect all attacks in the input phase. As I said, rest of attacks will be detected in the second verification. To discuss first verification, I should show a little more detail of distribution phase. In distribution phase, each value is calculated by this formula. Because the adversaries can adjust each term of the first formula by multiplying arbitrary values P1, P2, P3. This value can be expressed like that. Now we omit another value here. This verification passes through only if P1 is equal to P2 and P3 except for negligible probabilities. I will probe this next. The first verification can be said that verification of random value which has secret by addition such as alpha 1, and the reliable random value will be prepared by commitment. This is the detail of verification. Please note that adversaries can adjust R1, R2 in the same way as P1, P2, P3. Because the adversaries don't know small a, large A1, and large A2, we can see this equation as an identity regarding small a, large A1, large A2. Therefore, we can obtain P1 is equal to P2 and P3 from these equations. This is the goal of the verification. Next, I explain the detail of second verification. This verification is to verify the output. Now, we denote x as x prime if x is not reliable regardless of its validity. As I explained, this verification is to verify whether true output is same or not. Please note that alpha 1 and alpha 2 are reliable because these are obtained by commitment scheme. Now, we set these unreliable values as shown in the slide. These values can be adjusted by the adversaries. As I discussed in first verification, if first verification passes, we can say Q1 is equal to Q2 and Q3 is equal to Q4. Therefore, this verification becomes as shown in the slide. By deforming the equation focusing on small a, alpha 1 and alpha 2, we get this equation. Because the adversaries don't know alpha 1 and alpha 4, we can see this equation as identity regarding alpha 1 and alpha 4. So, if the adversary want to pass the verification intentionally, at least these two equations should be true. Therefore, if the verification pass, two outputs become same and they are correct. Our verifications can detect incorrect values intended by the adversaries. However, each verification will be passed with incorrect values unexpectedly. The probability is negligible because we consider large enough p and eta is a positive number. Next, security comparison. As shown before, we improved security of TS method maintaining its advantages. Our method can apply for any n which is equal to k or more. And our method has security against malicious adversaries, while TS method is only secure against semi-honest adversary. And we achieve information theoretical confidentiality and computational integrity. Next, efficiency comparison. Actually, our method is basically inferior to other methods in efficiency. This is because our method has some advantages regarding security, such as the limitation of n and k. However, we can say our method is round efficient in reconstruction. The number of rounds here is calculated in terms of the way of communication. First, TS method is only one round for reconstruction because TS method has no verification step in reconstruction phase. Second, SPDZ is 8 round in reconstruction because that requires a 4-round verification step twice in reconstruction phase. Next, our method is also 1 round because most of the values which are required for verifications are generated before reconstruction phase. So, in proposed method, solvers have to do is to send the required values to the receiver in reconstruction phase. This slide shows the detail of the difference of the number of rounds. As I said, SPDZ is 8 round because that requires a 4-round verification step twice. This means all multiplications and output are verified by 4-round protocol. This protocol utilizes commitment scheme, which requires some communication. On the other hand, proposed method verifies all inputs and outputs. Therefore, the values for verifying all inputs can be generated at any time after distribution phase, while the values for verifying all multiplications in SPDZ are generated after all multiplications are done. So, in our protocol, by generating the value for verifications before reconstruction phase, we can reduce the communication in reconstruction phase and achieve only 1 round reconstruction. Conclusion. We improved the security of TS method, maintaining its advantages. Our method is round efficient in reconstruction phase. But our method is not efficient regarding the computational complexity, communication complexity, and so on. So our future work is to improve the efficiency maintaining our security level. Thank you for listening.